Okay, everybody. So what we're going to do today is we're going to look at differentiability, which not a bad topic. Pretty easy actually, compared to some of the stuff we've been doing. Definitely one of the easier topics. So let's just get right into it then. So we've learned what the definition of the derivative is, right? And differentiability is a function differentiable, which I realize I just went around in circles and just said differentiable means differentiable. Um, differentiable means that the derivative exists. That's what I meant to say. So let's write a definition. So definition. All right. We say f of x is differentiable at a point. It's not how you spell point. At a point, x equals a, if f prime of a exists. That's it. Derivative exists, right? That's the derivative. F prime is the derivative. If the derivative exists, we say the function is differentiable. Okay. Now, a lot of times, we're not going to be talking about differentiability at a point. We're going to be talking about differentiability on an interval or just differentiable overall, right? So, right, if we say a function is differentiable on an interval, I'll say that a function is differentiable on, I'm going to say AB. Actually, I'm not. I'm going to change that. I'm going to say AB this way. It doesn't really make a difference here, but I feel more comfortable with that because if you have closed brackets, then maybe the function doesn't even exist on the other side of those brackets, and I don't want to think about that right now. So a function is differentiable on AB if, now maybe I shouldn't have used AB, but on interval AB if f prime of x exists for every x in AB, right? So differentiable on an interval just means the derivative exists everywhere in the interval, okay? And that's it, right? That's what differentiable means. So a couple of, I guess, easy kind of repercussions of this here are, let's see. So a couple easy kind of simple things you get from this right away is that so if, let's see, if a function is differentiable at x equals a. Okay, colon, what's that mean? So if a function is differentiable at x equals a, then we know, by definition, f prime of a exists, right? That's literally the definition of differentiable. But that means that this limit exists. Limit as x approaches a of f of what? No, sorry. Limit as x approaches, nope, try again. Limit as h goes to 0 of f of a plus h minus f of a over h exists, right? Because what I just wrote there was the definition of f prime of a. So, of course, if the first thing I wrote exists, the second thing I wrote exists. But that actually tells you more than you might think, because this tells you that, first of all, f of a has to exist. Okay, but then, no, not but then, I don't want to write that, I just want to say that. But then f of a must exist. Why? Because it's right there, right? It's right there in the formula, so of course it must exist. F of a must exist, and in fact, since we need the limit as h goes to 0 to exist of this thing right here, and h could be positive, which means you're on the right side of a, and h could be negative, which means you're on the left side of a, and somehow this limit works out to the same answer in both cases, then not only must this function value f of a must exist, but the limit actually as x goes to a of f of x must also exist. And maybe I'm not going to justify it right here, I'm just going to write it, but also as well, not only does the function value exist and the limit exist, but they end up having to be equal, which means that the function is continuous. F of x has to be continuous at, oops, I just accidentally threw my pen. Actually, you need f of x must be continuous at x equals a. Okay, and I realize again that I didn't necessarily justify all of these things 100%, but they're all true. Okay, function of differentiable, then all of those things are true. Now, what's that mean? Consequences of this are, or is, are. Consequences of this are. If a function is not continuous, then it is automatically not differentiable. If f is not continuous at x equals a, then f is not differentiable at x equals a. All right, that's really the big one that you need. Okay, f of x is not continuous at x equals a. All right. Yeah, that's fine. And that's usually, like, sometimes that's listed as a theorem. I don't know what I would call it if I was going to call it by a name, so I'm not. I'm just going to say, well, that's a fact that we should know. Okay, not continuous means not differentiable. So the way you're going to see that, the test, not test, but in the homework, is something like this. They'll just be like, is this differentiable? I shouldn't say this, I'll say f of x. No, I'll say g of x, why not? Is g of x differentiable at x equals 2, question mark, at x equals 3, question mark, and I'll draw a little function and we'll decide. 1, 2, 3, 4. All right, so there's a function, and that function is y equals g of x. All right, and so the answer to this question, or let's see, at x equals 2, differentiable, yes or no? Answer is no. No. How do we know it's not differentiable at 2? Because x equals 2 is right here, and the function's not even continuous, right? No. It's not continuous. Continuous, which implies not differentiable. All right. Now, what about at x equals 3? Now, I haven't really talked about what differentiable looks like on a graph yet, but x equals 3 is fine here, so it is. Yes. I'm just going to say yes. X equals 3 on this, stop moving. X equals 3 on this picture is right here, right? And there's nothing special about that point. Like, could you draw a tangent line right there? Sure, right? Like, there's a tangent line. What's the derivative? It's the slope of the tangent line. So if there's a tangent line there, sure, it's differentiable. Okay, so that's kind of the basic idea. You know, where is it differentiable, where is it not? Um, Now, we do want something better than what we just had in order to do this problem, right? We want a better understanding. So what I want to say now is, when is a function not differentiable? That's the big thing. So we've already saw um, one case. The case is not continuous, right? Not continuous means not differentiable. Why? Because if you're differentiable, you're continuous. So you can't be not differentiable and continuous. I'm going to do this all just at like 3. I don't know why, I just feel like it. So here's a function that's not continuous at 3, which means it's not differentiable. So when is a function not differentiable? 1, when it's not continuous. What else? Another time would be if there is a corner at the point. I'll say x equals a. Well, there goes my whole we're going to do this at 3 thing. Called it a this time. What a dummy. All right. So a corner, what I mean by that is if the slope changes there, right? At a point, if there's a sharp corner, then there is no derivative. And the reason that's the case is, remember what a derivative is supposed to be. It's supposed to be the slope of the function. And if you've got a corner, then that means on like the left side, you have this kind of tangent line. But on the right side, you have this kind of tangent line. Well, how could you have 2 different tangent lines there at the point? Well, you can't. Okay, they're not a tangent line then. So if the slope on the left is different than the slope on the right, there is no derivative, because the derivative is the slope. You can't have 2 slopes. Let's see. Slope on left doesn't match slope on right. That's the issue there. Now, a third thing that can happen is an infinite slope at some point. And there's several ways that you could draw that. So, don't know how well I'll do here, but let's say that this is the point we're talking about. And what could happen, is as you get closer to that point, it becomes vertical, and then it goes like that. And I'm actually going to erase that little dot there. So that kind of thing makes it not continuous at, I guess, 3. Now let's forget 3. Let's just call them A in every case. A. Okay. If there's an infinite slope. Now, infinite slope means vertical slope, because a slope is rise over run. And if it's vertical, that means there's some rise and no run. So you're dividing by 0. Okay. So that's going to be, let's see, just the graph is vertical at a point. Okay. Then there's no derivative there, because the derivative would be infinity, either plus infinity or minus infinity. Okay, and what else? Sometimes they say a cusp, which is kind of just a combination of the previous 2. So I don't even know if I really need to say it, but you know, we'll kind of say it, I guess. You know, maybe this is already covered. Cusp. And so when they say cusp, what they're talking about is, like if I put A right there, they're talking about something that does this. Okay, and you don't even really, like I said, need to list this as its own thing because first of all, right at A, it's a vertical slope. So that's one reason why it doesn't exist. And also it's a corner, right? There's a corner right there. So if it's a corner and an infinite slope, then of course it doesn't exist. We already said that that meant it doesn't exist. Okay? Yeah. Also be aware that there are many kinds of discontinuous graphs. So I drew a jump discontinuity for this graph, but they're not always jump discontinuities, right? So like if I have an example, I'd say continuous at x equals 2 question mark. Oh, sorry, differentiable. We were talking about differentiable. Differentiable at x equals 2. What do you think? No. Why not? Because it's not continuous. At x equals 2. Okay, so there you go. Those are some of the cases where a graph would not be continuous. So you just need to be able to identify them on a graph. One thing I will say is that you can have things like piecewise defined functions, and they're still differentiable. So here's an example of something that's differentiable. Example. This is a piecewise graph that is differentiable everywhere. All right, so let's say f of x equals, and I'm going to say 0 when x is less than 0. Yeah, let's move that, sorry. No, that's fine, I want to leave it there. And then I want x squared when x is greater than or equal to 0. Okay, and so what this graph looks like, if you draw it, is this. So you've got 0, no. So you've got 0 here. And so on the left side, the function is just 0. So on the left side of 0, this is what you have. Okay? That. Now on the right side of 0, you have y equals x squared. That's a parabola. So it goes through 0, 0, and 1, 1, and 2, 1, 2, 3, 4, like this. And it goes up. That kind of looks very steep, but it doesn't, that's not vertical, right? That's just a parabola. It just happens to look pretty steep here. All right. So there you go. There's the graph. And it is differentiable because what happens is this is a 0 slope, but when it switches to the other function, the other slope also starts out 0. So what happens is you have, I'll draw it here where I can draw it a little easier, right? That's 0, but then on the other side, it starts out 0. So it's smooth there. There's no corner. There's no corner right there, even though it's a piecewise defined function. Because on both sides, the slope is the same. Slope is 0, right? So there's no hole in the graph to make it not continuous. And it happens that the graph on the left and the graph on the right match up in terms of the slope. And so it's differentiable, right? There's a tangent line right there. It's perfectly fine. Okay. Now what else? I do want to write something. This is kind of going back a little bit now before I started drawing graphs, but just talking about this thing, if a function is differentiable at x equals a, blah, blah, blah. Just because they ask you kind of a weird question in the homework, right? So here's an example. They say, suppose limit as h goes to 0 of g of -2 plus h minus g of -2 over h equals 11. Okay, and then they say, what must be true? And they give you choices here, and you have to select which ones apply. I'm going to save you and take you with me. Oh, sad. Okay, I figured it out. Okay, duplicate, move. Duplicate, move. Duplicate, move. Oh no. Duplicate, move. Okay, 5 of them. 5 of them? 5 of them. Okay, so there's 5 things. And so they say the 5 things are limit as x goes to 3 of g of x exists. Then they say limit as x goes to 11 of g of x exists. And then they say g of x is continuous at x equals -2. Then they say the limit as x goes to -2 of g of x equals 11. And then they say the limit as x goes to -2 of g of x equals g of -2. Okay, so they give us these 5 things, and they're saying which ones are true. And so we need to understand what we're being told with this. So what does this statement say? So first thing you need to understand is on the left, what is that? You're supposed to recognize it as a derivative, right? This is a derivative. It's a derivative. Which derivative? It is g prime of what are they plugging into the derivative? They're plugging in a -2, right? That's the a. So it's g prime of -2. Okay. Now what is the result of g prime of -2? Well, that's this. So it's 11. So this is what they say. Like, this is the real information that they just gave you. They told you that g prime of 2 is 11. That's what they were saying with their statement. What are the implications of this? Well, the derivative exists, right? That means it's differentiable. So g is differentiable at x equals -2. That's not on the list, but I'm just writing that. Okay, g is differentiable at x equals -2. But if g is differentiable at -2, then g is continuous at x equals -2. Because if you're differentiable, you are continuous. Okay, so where is that? Is that on here? Yeah, actually it's right here, right? That one's true. G is continuous at x equals -2. All right, now what else is true? If it is continuous, that means that the function value equals its limit. So if it's continuous at x equals -2, by definition, the limit as x approaches -2 of g of x equals g of 2. And that's the definition of continuity. All right. And so, oh, sorry, that should have been -2. And that's this box. Okay, now what about the other boxes? What's wrong with all of the other boxes? So this is wrong because they're talking about x goes to -3. X doesn't go to -3. X equals 3, wrong. Nobody's talking about x equals 3. Same thing with this one, right? It says limit as x goes to 11. X equals 11, wrong. That's not what we're talking about. Like the result is 11, but that's not x is 11. Okay, so that doesn't mean anything. So that's why those are wrong. Now what about this one? Well, this one says the limit as x goes to -2 of g of x is 11. No, right? This is not 11. This is 11. Why would this little one be 11 just because this big one up here was 11? No reason for that. Okay, so they're giving you like nonsense statements, and that's just not what it says there. Okay, so this is the way you want to progress in your logic. That's a derivative. That means it's differentiable. That means it's continuous, and specifically, this is what continuous means. Okay, and that's how I get the 2 that I checked. All right, so that's like kind of algebraic what differentiable means. Okay, there's another one of those on the homework. Easy peasy. One thing we have to do is we have to be able to draw derivatives still, just like we kind of talked about in the previous section, drawing derivatives. So let me actually find one, a good one, hopefully. Blah. I will say that a lot of this homework is literally like looking at a graph and just going, like they say, which ones aren't, or sorry, which one is differentiable, and you're just like looking for all these things. If you see them, then it's not differentiable. Those are really easy. All right, but here's one slightly harder problem here. Here's an example. This is really kind of from the previous section, but we want to be able to interpret it here. So given this graph of f of x, identify, we're going to have to draw it, but they say identify the derivative. So identify the graph of f prime of x. Okay, so they give you the original graph of f prime. So I'm going to go call it 2, 2. There's 2, there's 2. We don't care, but there it is. And I'm going to draw a line like this. Okay. And then I'm going to draw another line. Oh no. I hate it when it moves at the very last second. Okay. Hopefully that's good enough. All right, so this is a graph of f of x. And we want to draw the derivative. That must be -2, sorry. Okay, that's x, there's y. All right, so first thing is first. Now we said that a graph is not differentiable if it has a corner, but the only place where it's not differentiable is at that corner. Like right here, it is differentiable. It's only not differentiable at -2. So at -2, there's no derivative. But everywhere else, there is. So what is the derivative? Remember, the derivative is the slope of the function, right? Derivative equals slope of function. It's also the slope of the tangent line, but I drew straight lines, so they are their own tangent line. So derivative is slope of the function. So let me ask you this. In this section of the graph on the left here, what's the slope here on this part? I was careful to draw these so it was a slope that you could understand, right? So this is like one box down, one box over. Whoa. I had no idea I could do that. A miracle is occurring. Holy crap. Okay. What just happened? What's that slope? What I was trying to draw here... Oh no, what is... Okay, now, this isn't a miracle anymore. This is annoying. Delete. Sorry. I drew the slope so it was 1 down, 1 over, 1 down, 1 over, 1 down, 1 over, 1 down, 1 over, right? 1 box, 1 box, 1 box. So what's that slope? You should be able to recognize that that's a slope of -1. It's definitely negative, right? Down 1 over 1, down and to the right is a negative slope. So it's -1. So that means over here, if I want to graph that, I just go to -1 and there it is, -1. And it's -1 over this whole region, and that's why it's -1 here. It's just staying at -1. Okay, now what about the right-hand half? What's the derivative over here? Or what's the slope over here? What's the slope in this part? Again, I tried to draw it so it was easy to see. So like there's a point, right? And we go 1, 2, 3, up 1. 3, 1. And then 1, 2, 3, up 1. 3, 1. So the slope is rise over run. So the rise is 1 and the run is 3. So the slope is 1/3. So that means you come up here to 1/3, which kind of looks like a half there, but 1/3. And that's your slope. I mean, if I could draw it a little better. It's hard to draw 1/3. Okay. And this needs to be empty. Okay. So that's what it looks like, right? This is at y equals 1/3 because that's the slope on the other graph, and this is at y equals -1 because that's the slope on that piece. And I'm using open circles here because at -2, if this is -2, at -2, there is no derivative because right here there is a corner, right? No derivative at the corner. But everywhere else there is a derivative. So this is a graph of the derivative. Okay? And yeah, there you go. Okay, I think that's it actually. I think that's it for this relatively short section for us. Okay, so that's it. I'll get another lecture up soon. That's it for now.